Welcome to my YouTube channel. Today I'll be talking about one of these things. It is a zone valve actuator head for a central heating system. Many of the viewers are familiar with these things, I should think. So I won't go into too much detail. This one's a Siemens DVA2 /5, and it just failed and didn't divert the hot water into my central heating system, or rather it was stuck on, and the central heating system was on all the time, or apparently it was. Well, there we are. I had a few misnomers about the way these things work. Okay, so I thought first of all I'd show you a diagram of my setup. So without further ado, we'll put this diagram in here and we'll explain some of these things that I've written out here. First of all, we have to talk about this bit here, the boiler programmer. I haven't drawn in any connections here because I wasn't certain of how the boiler is wired to the rest of the circuit. I know about some of it, but not all of it. So that is as is, but it doesn't show any connections elsewhere. That's been drawn deliberately because I simply don't know, and it's not a very good advert for this video, but that's the way it is. I was a telecommunications engineer, and we used to buzz wires out, so you can look on YouTube about what buzzing out wires is, but basically it's to find continuity on wires when you don't know where they're going, and you must make certain that there's no dangerous voltages on the wires when you do it. You can use a multimeter, but in my case the leads to my multimeter are not yards or meters long, because you should put one end of the multimeter on one end of the wire and then the other end of the multimeter on the other end of the wire. And in my case, in my central heating setup, the wires in one of the units, connection units, is a long way away from the other. So years ago, when we were telecommunications engineers and we were on tag blocks, wiring tag blocks, we used to make up a buzzer with a battery with two long leads coming out with clips on, and we'd clip the buzzer on the tag block where the wires were, or a wire, and then we'd run the lead, which would be very long sometimes, to the other end of the cable to see where it was going and what it was, because it would buzz, and that's why the term is used, buzzing out wires, because the buzzer would buzz. It wouldn't make a funny noise like a modern multimeter, because there weren't such things in those days. The other thing is that this here, okay, is I'll call it, the terminology I use is a chocolate block, and it's just a tag strip, and lots of people on the internet have shown these things what they are. They don't say sometimes why they're called chocolate blocks, because in the early years, in the 1950s and perhaps a bit earlier, they were made out of kind of Bakelite, which was a dark brown chocolate colour, and you can break these apart in bits, okay, just like you can a bar of chocolate, hence a choc block. So I'll be calling this a choc block. So there we are. So that's a bit of history. Now let's get on with this very quickly. The first thing to note is what is said. Let's just move that there, up here, okay, and I'll read this. Inside this, okay, inside there is a cam operated micro switch, and I'll just read this to you. A cam operated micro switch within the motorized valve actuator unit. When the zone valve is fully open, the micro switch sends 230 volts to the boiler, which ignites the burner and operates the central heating pump. And that is really the essential part of this video. So the motor in here turns around, and at the back here is the actual valve itself in the pipe work, as many of you probably know, and it has a direction of flow A. If your boiler is this side, this will be A, and if your central heating system is this side, this will be B, A, B. And the valve is at the back, and it's on a spindle, and the spindle slots through into there, like that. And this particular one has just a sort of metal slot, like a screwdriver slot in it. And so the spindle has, well, this hasn't got a slot, it's just a metal, let's show it, a metal piece there, which slots into what looks like a slotted spindle on my system. So you can't use any old thing, any old one, to replace this one. You've got to use one that has that type of connection in it. Otherwise it just won't fit onto your zone valve, 2-port zone valve in my case. The other thing to note is it's got clips on it here and here, and the whole thing is simply designed to just clip into the zone valve proper, and so this motorized head can be just pulled off and replaced if it goes wrong. So that's that. Well, to continue, the thing that I didn't realise, and it's the principal reason why I'm doing this video, is it might be a surprise to you, but down through the years I've always considered a synchronous motor, which is what is inside this, a synchronous motor. It doesn't have any brushes in it, and it's synchronous. The word synchronous is because it synchronises with the frequency of the mains, and its speed is proportionate to the frequency of the mains. So in this case, in this country, 50 Hertz. So this is what happens, and I didn't realise that these synchronous motors are specially made, and I'll read this to you just to explain it to everybody if you didn't know. The synchronous motor within the zone valve actuator stops by stalling against a mechanical limit when the valve is fully open. So the motor goes, so the motor goes round, it turns the valve spindle in the back here to the open position, and when it's fully open, it's held, when the valve is fully open, it is held in place by a live from the thermostat. When the mains is removed, when the thermostat switches off, an internal set of springs returns the valve to its closed position. The motor is designed to be stalled indefinitely without burning out due to its high impedance windings, or to some of you, like just high resistance. It's got a lot of windings, there's a lot of wire, a long winding in it. It's got a lot of wires in it, length of wire I should say. One wire, but it's very long, and it's installed indefinitely without burning out due to its high impedance windings. For a detailed look at how it works, please see this link, and I hope that you can see that link there. And that link is to John Ward's very excellent YouTube page, channel, where he explains exactly all about how this works, and he's taken it apart, and it's a very detailed and very clear and precise explanation, one of the best I've seen on the internet. Thank you very much, John, for for doing that, and I acknowledge here right away your excellent knowledge in all matters of electrics. So that was really the point. The point was, I was worried in my ignorance that when this motor stalls, and the rotor with a cog attached to it physically stops, it is designed to be able to cope with voltage and current still being on the motor. It gets hot, it's about 4.5 watts, but it's designed to dissipate that heat and that power. It's designed to dissipate that heat with the motor housing, and the windings are of a sufficiently high resistance to limit the current. If they weren't, the whole thing would burn up very quickly. So there we have it. Let's just explain the circuit very quickly. It's all been explained by John Ward on his excellent YouTube channel, but I shall just do this for folks who may have a similar system to mine. And the principal thing is that my system has 2 zones to control, zone 1 and zone 2. Zone 1 can be your, in my case, a airing cupboard, radiator and perhaps towel rails or something, which you don't want to be having heating. You don't want it heated up and working in all the time in the winter, say like your central heating radiators are. So that would be, it could be your upstairs radiators in your house. It doesn't really matter. And this zone 2 in my case is all my radiators. So you want to be able to switch them independently with these motorized valve heads. Okay, and they are controlled from thermostats here and here, and in this case zone 1 thermostat, if you can read that, and zone 2 thermostat. Now all across this diagram you will see SL, and that stands for switched live. And if you read the note here, it says SL denotes a switched live. It only becomes live after 230 volts has been applied from a permanent live part of the circuit. I keep saying 240 volts because of course in this country nominally the mains is 240 volts, but it can dip down to as low as 220 or even lower sometimes. Such is the quality of our wonderful electrical supply system these days, but normally it's nominally, most of the time it's 240 volts. So you'll see 230 volts here, but you see up there it says 230 volts, but actually the mains in this country is nominally 240 volts. Anyway, that's an aside. So SL denotes switched live, and that's important because if you test it with a tester or one of these, don't recommend you using one of these, but these mains tester screwdrivers, and you stick your finger on there and put the live on there, and you have to be careful. This is insulated here, you don't slip and electrocute yourself, but when you put that on the switch live circuit, it comes on only when there's switching. It's been switched on from some other part of the circuit. It's not always live. It'll only be live when it's switched on. So that's important to remember. So what happens in the case of, say, this motorized valve here, okay, is that this micro switch up there, okay, comes on when the motor turns on a cam, and the cam, you know, it's got a lobe on it, and that lobe is hitting a micro switch which then operates. So when the motor reaches its reaches its limit and it's turning the valve on in the pipe, it hits the cam hits the micro switch, and it then sends a live switch live out to a connection in the boiler here called SL, and that is what fires up your boiler and switches on your central heating pump or whatever. So that is what happens there. So obviously when the valve is in position and it's open and it wants to allow a flow of hot water through, you want to have your boiler switched on, and that's how it switches it on there through this wire here, if you can see it. And I've written there SL switch live to boiler. Perhaps you can see that. So the other thing to note is that there's an industry standard cable color wiring on these things here. Okay, and the colours, there's usually 5 wires. There's the green and yellow, which is green and yellow, which is earth. There's the blue, which is mains neutral, brown, which is mains live, and then these two here are grey and orange, which are the connections to the micro switch, and the live would come in on this grey wire, I think, a switch, and then it would switch over onto this orange wire, which will send the mains voltage out to the boiler. So that's that. So, and that is denoted by these colours here, grey here and orange here, and of course the mains coming in here. So really, the other thing to note and to remember about these central heating circuits is that invariably, and in this case my circuit, is that the thermostat has a permanent live connected to it, and you'll see it comes from your 13 amp what we call fuse spur. It's basically a circuit breaker. It's just it has got a fuse in it, and it's a switch, and it is the supply of the mains to the boiler and other parts. So this permanent live brown wire here is permanently wired to the thermostats. Okay, and you'll always find a live on there. And when you turn the thermostat on, this switch operates, and the switch live comes around on this. In this case, you see it's a grey wire, but it might not be. In my case, it's actually a black wire, but in the case of my installation. But anyway, that switched live comes around and feeds in on this chocolate block, and then it goes through to one wire, right, which is fed in to the motor of your zone valve. That's the motor. Okay, so the motor is switched on, and it turns due to the thermostat being turned on or off, or whatever the case may be. When the thermostat goes off or you turn it off, the supply to the motor is cut and it stops working. And at this point, I would like to have seen as a general principle that these motors are switched off in both, you know, when they've operated, to switch off as well, but they don't. The whole principle of them is they stay on, they are stalled, but the power remains on them while the thermostat is in the on position, is switching, cooling for heat, as we say. So, and they do get hot, I tell you they do. They're designed to. It was a worry to me, and incidentally it's my considered opinion that these fail simply because perhaps quality assurance from some manufacturers is not what it should be, and after a few years, okay, they just fail in some way. heat, in my opinion, heat really is a big no-no. The lower the temperature you want to run you should run things at, the better it is. Lower temperatures are much better than higher temperatures. That's just a general engineering point, by the way. But still, there we are. These things have been going for years like that, and people have accepted the fact that they get hot. Well, there we are. I don't accept that fact, to tell you the truth. I think that the whole thing is a little bit let's manufacture something that is less than 100% reliable, or may not be. But anyway, that's another thing. The other thing about my system is that, as I showed you earlier, mine's an old one. It's very old. It's a Siemens DVA2 /5, and really you should replace this zone motor, this motor head, with one of the same model, or a third-party one that is got the same spindle connection at the back. Okay, and the only one I could find for my Siemens DVA2 /5 was one of these. It's let me show you. Can you read that? It's made in Spain, as you can see. P motorizada, Spanish motorized part. Okay, and it is exactly the same, made by Orkli, and there's a couple of companies that supply these on the internet, and these zone valves from Orkli have got a red case to them, not a silver one like this. They have a red cover, as you can see in the diagram, and they are about half the price of these, right? Half the price, at around 60 odd pounds, perhaps just over 60 pounds with postage on the internet, and I had to buy this one. So if you've got one of these that fails, buy one of these. Now that's not an advertising thing, really. It's just sensible to get one of these. It might be advertising, but that's another thing. Right, so that's it really. I'm about to fit this into my central heating system. A few points to remember: if you do this at home, you must switch off at the fused spur. You see it on the wall and have a little fuse socket in it, or a switch, or so. Switch it off. Make sure your mains is switched off for the boiler. Do not attempt to fit one of these into the chocolate blocks, or wherever it goes with the mains on. Please, you'll electrocute yourself perhaps. Okay, or worse, you might connect the wrong thing up and ruin your boiler in some way, or the timer in the boiler or something, because of connecting something up wrong here. I don't know, it might be, who knows. So there we are. I'm about to fit this in, and the best thing to do with these is to take one wire off the chocolate block at a time. Where are we? Just take one wire off at a time and put the new wire in. Okay, so you don't get confused. Don't take the whole lot off at once unless you do a video of it, or a photograph of it. Okay, I think that really covers everything. Look, thank you for watching. Some of this might be obvious to you, okay, but there's the diagram. If you can copy it off, do what you like off of my YouTube channel. Okay, and at the bottom of the, let's get this right, at the bottom of my YouTube channel, okay, down there at the bottom of my YouTube channel, you will see the link here, okay, that you can click on to look at John Ward's explanation, and he's got other things there other very useful electrical installation videos on his YouTube channel. Thoroughly recommended. He's very precise and much quicker at explaining things than me. Anyway, thank you for watching.